So, Chapter 7, the quantum mechanical model of the atom. And we've got a flashing screen again. Okay. There we go. So, the beginnings of quantum mechanics. So, quantum mechanics started in the early 20th century. That was, early 1900s. Before that, we believed, fairly reasonably, I think, that the laws of physics that apply to things like baseballs and other objects that are large enough for us to see also applied to very, very small things. But they're famous because of this. A lot of physicists, mainly, were studying the very, very small particles, atoms and electrons and the other subatomic particles. And what they found was that those very, very small particles are not subject to the same deterministic laws of physics that the larger objects are. For, say, a baseball, its present condition determines its future condition. If you put a baseball in a pitching machine and you have the machine pitch the ball, you put the baseball back in there and you have it pitch it again, it's going to follow almost exactly the same trajectory and end in the same place, go the same speed. This is the sort of thing we understand. For these subatomic particles, the present condition does not determine the future condition. So if you were to shoot an electron, maybe you had, instead of a pitching machine for baseballs, you had a pitching machine for electrons. Stick an electron in there and you pitch the electron. Okay, there, went over there. Do the same thing with the electron again. It's not going to go the same place. It's going to go somewhere else. And you can't predict exactly where it's going to go. This isn't right. And people who found this are like, wait a minute, what's going on? Okay, quantum mechanics is disturbing. So I'm sorry. I might make your head hurt today. So the absolutely small, or the quantum world, is what we're talking about, the very, very tiny particles, the world of electrons. It behaves very differently than the larger macroscopic world, things that we can see. So these absolutely small particles, like electrons, can actually be in two states at the same time. Not like California and Nevada, but two physical states. As an example, a radioactive nucleus can simultaneously be emitting a particle and not emitting a particle. Does that seem wrong? Yeah. How can that happen? Well, that's a hard one. That's a hard one. Electrons are incredibly small. I mean, trying to think about how small an atom is pretty tough. Electrons are much smaller than atoms. So if you think about a single speck of dust, a little particle floating through the air, a single speck of dust has more electrons in it than the number of people who have ever lived on the Earth. That's a lot of electrons. Electron behavior is important because the behavior of electrons affects the behavior of atoms. The behavior of atoms affects the behavior of matter. Why is this bench black and shiny and hard? Well, the electrons have something to do with it. So we have to understand a little bit what electrons are doing. So electrons can exist in two different states at the same time, and the problem is that if you observe what an electron is doing, which we can't do directly because they're too small to see, but we can do that indirectly. If you observe it, that causes its behavior to change. It acts differently when you're looking at it. What? How can electrons aren't cognizant of what's going on? They're not alive. They're not sentient. What's going on? It's hard. It's hard. So even just shining a light on a beam of electrons changes what they do. So are we going to come to a complete understanding of this today? No, we're not. I don't think anybody completely understands it, and I certainly don't, and I don't actually even want to. I'm okay with just knowing enough to explain the other stuff. So, have you heard of Schrodinger's cat? is kind of a joke in some ways. This was a thought experiment, okay? No cats were harmed. There was no actual cat, okay? It was just a thought experiment. And it's a thought experiment to explain how this strangeness of the quantum world does not translate to the macroscopic world. So I've got a couple YouTube videos here that we're going to watch.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrodinger's Cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
Okay, did it give you a headache?
Well, slow that down a little bit. I was like, trying to keep up.
Yeah, he talks really fast. So the cool thing about YouTube is you can watch them at a slower speed, right? So you could go, and this will be on the, well, I mean, it's in the video, but it will also be separate as a video in the playlist. And that's from a site called Minute Physics, which has a lot of pretty good stuff. Notice no cats were harmed in the making of this video. And then here's another one. And this guy also talks pretty fast. But
hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrodinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. Then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flaws of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it, wondering what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat A cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrodinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrodinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrodinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Okay, so that's another great website. They actually have a bunch of different videos. I think there's one channel called Crash Course Chemistry, and that guy is, he's just easy to watch his videos. Okay, so here's my interpretation of Schrodinger's cat, because I'm thinking, well, maybe if you hear it 3 times, it might make a little more sense. So electrons, other quantum objects, can be 2 things at once. They can be a wave and a particle. They can actually, in a sense, be in more than one place at the same time, which is like really hard to understand. But if you observe them, then they have to be one or the other. You can't observe them being all these things at the same time. And Schrodinger's cat, the experiment, is to point out how absurd this is. Because with something that's large enough to see, like a cat, it can't be both dead and alive. It has to be one or the other. With these quantumly small objects, they can be in different places at the same time. They can be in different states, different conditions at the same time. And when we observe them, we force them to be in just the one thing. Okay, so questions about Schrodinger's cat, or this idea of superposition?
So then, when it's saying that they're in all these different states at the same time, that's like theoretically, or they actually are?
Well, all the evidence we have says that that's the case. Yeah.
But when we observe them, is it because light has an effect on them? Because we need to see light.
That's one of the things that's the hardest for me to understand is how is it that us observing it changes the behavior? That's probably my biggest problem with it.
So where the theory come that they're in all these different states at the same time?
What was the question part?
So then where did the theory come from?
Where did it come from?
Yeah, that they're in all these different states.
Well, we're going to talk about a couple of experiments, actual experiments, that kind of demonstrate how electrons can be both a wave and a particle, and how they behave like particles here and they behave like waves over there. So you feel like your mind is like getting ready to explode, perhaps? Like, what the heck are we talking about here? To make you feel a little better, here's a couple of quotes from scientists who were working on this. Niels Bohr, said, "Anyone who is not shocked by quantum mechanics has not understood it." So if quantum mechanics doesn't bother you, then you have no clue about it, basically. Schrödinger saw his picture. He's the guy who came up with this cat experiment. He wrote, "I don't like it," referring to quantum mechanics, "and I'm sorry I ever had anything to do with it." You know, when you're a scientist and you're investigating things, sometimes you discover things that you don't like. Like, I don't like this. I wish it was some other way, but it is. Albert Einstein, you've heard of him. He was also involved in this, and he attempted unsuccessfully to disprove quantum mechanics for the rest of his life. He didn't like it either. He said, God doesn't play dice with the universe. So he's like, you know, I don't like this. I'm going to try to prove that this is not the case. Couldn't do it. So we're kind of stuck with it. Why do we even care about this? Well, this is a theory, a model that explains electron behavior. It explains how electrons exist and how they behave in atoms, and that's important to us because it helps us to predict and understand the properties of atoms that are directly related to the behavior of the electrons. So this helps us with questions like, why are some metals, some elements metals and others are not metals? You know, why is carbon a non-metal and iron is a metal? Why? And why are they all like grouped in the periodic table? And why is the periodic table that weird shape anyhow? Why does fluorine gain 1 electron when it makes an anion and oxygen gains 2? Quantum mechanics explains that. Why is hydrogen gas very explosive and combustible, whereas helium gas is not? They're right next to each other in the periodic table. What's up with that? And there are a lot of other periodic patterns, and they are all explained using quantum mechanics. So we have to at least understand a little bit of this.